Hello, everyone. I'm going to talk about the AMOC and its relationship to DO events. But first, I must acknowledge my collaborator, Florian Sevellec, who worked on this project when at Yale as a postdoc. He's now at National Oceanography Center in the UK. All right, so with this talk, in the spirit of one of the previous talks by Eric Wolf, we are trying to get the simplest possible model for DO events. And what we want to reflect this chaotic millennial variability during the glacial interval, and then a relative stability of the Holocene. And our hypothesis for millennial variability is quite simple. We think that the AMOC becomes unstable during glacial intervals because of the southward expansion of sea ice and corresponding shift of deep water formation. This shift of deep water formation displaces the AMOC relatively to the dominant surface P minus E field. Precipitation, basically freshwater fluxes, and that makes the system unstable. Going back to the Holocene, it becomes stable again. And our approach is a modified Howard-Marcus-Wilander loop model. And it's the simplest model for the AMOC you can think about, one step further from a box model of Stommel. So the AMOC, well, we know it's circulation that with most of the mass exchanges occurring in the upper ocean and then return deep flow. And in that sense, it's a loop. And this is this loop schematically. When water flows in the surface branch, it experiences freshwater fluxes, E minus P, whatever. In the deep ocean, it's largely just advection. And it's a simple loop, and so we can close it. And really, in the simplest form, we can represent it as a rotational circulation with respect to some center in the middle of a basin. And this circulation experiences freshwater and precipitation and evaporation fluxes at the surface. So in simple terms, this is the loop model. Go into the equations. In this modified loop model, we have three equations for the rate of change of overturning, the rate of change of anomalies in ocean horizontal, north to south, and vertical bottom to north salinity gradients. And that's it. So we have the overturning, and we have horizontal and vertical salinity gradients. The temperature would come up later if we want to expand this onto effects on atmospheric temperature. But for the AMOC, we have just these three variables. And some other variables here, mean ocean overturning rate, omega naught, so it's mean circulation with respect to which we'll have our oscillation. And we have forcing. We have a buoyancy forcing or torque for the overturning induced by salinity anomalies. And we have forcing due to freshwater fluxes at the surface. We actually have two components that project onto the horizontal and the vertical in the simple rotational model of the AMOC. One thing, what's nice about this model, there are not so many tunable parameters. You actually don't need to tune it. You just plug it in, for instance, mean overturning rate for the ocean. There are some damping terms which you can estimate from, say, ocean GCM. And then there are mean freshwater fluxes. That's it. So, and now we go back to this idea of stability and instability during glacial interglacial times. As one of the previous speakers emphasized, there is a shift of sea ice cover. There is a mean shift in sea ice cover during glacial times and then a retreat during interglacials. Associated with that, there is a shift in deep water formation. And you can see, for instance, in this schematic picture from an intermediate model, this shift of AMOC during the glacial interval. We don't know exactly how much this shift was at 10 degrees, 15, 20 degrees, but there is a clear shift like this of deep water formation. And we can use this in our loop model by simply changing the relative structure of freshwater fluxes that our overturning experiences. And in the simple approach, we simply shift the basin of the MOC. So this is our basin of the MOC. We shifted southward during the glacial interval. And we can do it continuously, going from, say, the peak of interglacial to the peak of glacial, just shifting this basin and, in effect, changing the structure of mean freshwater fluxes. We can do it to a large extent, or we can do it just a little bit. And that would change in the model with two projections of freshwater fluxes, F onto the horizontal and vertical. So now I'm ready to show you some results. So these are the observations. And now we run the model, shifting this mean sea ice extent and changing the location of deep water formation. And this is what we obtain for the ocean overturning rate. So this is this gray line is our sea ice extent. So it varies from 70 to 56, but you can do a different range. During the Holocene, it's completely stable, and then during the glacial interval, we develop this chaotic variability on millennial timescales. It's obviously not exactly like what we observed in the observations, but it's very like the observed one, and it's chaotic. Actually, you can do a blow up and you can do different realizations, just slightly changing different, slightly changing initial conditions. We can obtain different realizations with DO events occurring at different times and having different periodicity between neighboring events. So if we do the power spectrum of the observations, this gray line here, we can obtain this peak. This peak corresponds to the two DO events, to this millennial variability at about 1500 years period. And our simple model really captures this peak. You can see here, without not much tuning, actually there was no tuning at all, we obtain this peak, and even the secondary peak is captured. We don't capture anything on a longer time scale. We don't have Heinrich events, for instance, and so the model and observations disagree at time scales at 10,000 years, for instance, but at the time scale appropriate for the DOA, for DO events, the agreement is quite nice and accurate. So the mechanism of oscillation, well, it goes back to ideas of salinity advection feedback. Suppose there is a weakening of overturning that reduces the salt transport to the north, a further weakening of oscillation due to positive salinity feedbacks. At the same time, salt accumulates in the upper ocean, gradually decreasing ocean stratification, and when stratification becomes unstable, ocean overturning reinvigorates. Then the cycle repeats. And apparently during the glacial interval, the salinity feedback is just stronger because of the shift of deep water formation that allows more, that gives rise to more instability. So we went further and tried to produce time-dependent attractors of the system behavior and it's the so-called Pullback attractor. And the idea is we have a time-dependent attractor. We run a large set of initial conditions that converge to an attractor at a given time t naught. And so we obtain different attractors for different states. And for the interglacial state, think about the Holocene, it's just one point, one stable state. But for a glacial state, we produce various chaotic attractors with various, and a pullback attractor here basically gives you a probability to find your state in this phase space diagram. So why is it this chaotic during the glacial state? Well, if you do a simple stability analysis of the system, during the in a glacial state, you find three unstable steady states with largely thermally controlled, zero overturning, and salinity controlled. And the system wanders about around these three unstable states, producing this chaotic behavior. So I have a movie of this attractor, which I may try to. Oh, okay. So this is a movie of how the system goes from steady state to chaotic attractors, and the top subplot is basically the expansion of the sea ice. So this is the glacial state here. And so you go to the last glacial maximum and then deglaciations. And during this time, you are going through all these different attractors. And that gives you this unstable behavior with somewhat different characteristic of variability along the glacial cycle. So I'm almost at the end. So the summary here. We have formulated this simple, and it's as simple as it gets, a simple AMOC loop model, which reproduces the observed spectrum of millennial variability, talking about DO events realistically. And the key parameter in the model that makes the system unstable is this southward shift of deep water formation associated with sea ice expansion, and it makes the AMOC unstable, but only during glacial intervals. And then stability comes to this three steady unstable states, and the system basically wanders about those states, giving rise to chaotic millennial variability of the dual type. Thank you.
Do you have any questions? Okay.
Are there intermediate states where the behavior of the system is strictly periodic? What's the reason behind it?
There is, if you, maybe I can just plot the movie, try to run the movie again. Okay. So there is a very short period of time where you have basically a cycle, and that's where you have periodic behavior, but it's very, very small parameter range, very short parameter range when you go to a full chaotic regime. Yes?
The question is why DCMs seem to not do these things. So far, DCMs have the tendency to be really stable, so it only wants to be stable. Even in glacial. So what is your opinion of that?
Well, first of all, again, I have to emphasize that for the modern state, we have completely stable state. So for the glacial state, the question is how strong this instability. If the instability is very strong, like in this model, we can observe it. If the instability is very weak, it may be really hard to do it in a LGM type, for instance, simulations, you really need to run your model for several thousand years to develop this instability. That's one of the reasons. And actually, I know about some of the simulation where people run the coupled model for like 3,000–4,000 years, and they see regime shifts of MOC that may be reminiscent of what we find here. Yes?
From the 1,500 years, our planetary analysis, but you said you didn't do any tuning. I was wondering if you do change some of those parameters you might tune. How sensitive is that result? How much is it?
Basically, what you saw in that movie is everything what you get. So changing parameters, we basically, some of the tuning parameters in the model, we actually moves along this diagram, that's it. So in principle, you can tune the parameters to kill the entire instability, but it's very hard to do because then you don't really get this glacial interval, this idea of deep water formation shifting southward. So if you see here, we used like 15 degrees shift, the maximum shift in MOC about 15 degrees. If you go, say, for a shift for 5 degrees, we still get all these regimes. That's the sensitivity.